Asia's technology race is no longer just about who has the biggest AI plans, the cheapest EVs, or the strongest factories. The more practical question is whether the system underneath that growth can carry the load. That pressure is now showing up in very different places. Energy costs in Southeast Asia, heat inside 3D stacked AI chips, long lead times for power semiconductors, tighter US trade audits, a shortage of vehicle-carrying ships, and an early India-Japan defense co-development effort. These are not one story, but together they suggest something important. Asia's next phase of growth is being shaped as much by constraint as by demand. Start with Southeast Asia, where the AI infrastructure boom is creating a clear divide rather than lifting the region evenly. Vietnam, Malaysia, and Singapore appear better positioned because of their links to technology exports and AI-related hardware demand. Thailand and the Philippines face more pressure, largely because they are more exposed to energy import costs. That matters because the AI build-out is not only capital-intensive, it is also energy-intensive. So the gains do not flow evenly across ASEAN. Economies tied more directly to the physical AI hardware stack may benefit more, while those more vulnerable to energy price swings may feel the strain. There's no single ASEAN AI story here. There's a split one, and that split may persist as long as AI infrastructure expansion depends heavily on power, equipment, and industrial capacity. That energy intensity leads directly into the technical limits inside AI hardware itself. In advanced 3D stacked AI chips, packaging specialists increasingly describe heat dissipation as the main bottleneck to further performance gains. The logic is straightforward. Stacking compute and memory more closely together improves speed and bandwidth, but it also concentrates heat in a smaller physical area. At some point, that heat becomes a constraint on performance, reliability, or both. This is why AI scaling is no longer just a matter of adding more transistors or stacking more layers. It is also a thermal problem. Two possible directions are being discussed. One is co-packaged optics, which would integrate optical interconnects directly with the chip package. The other is system technology co-optimization, where chip design and system architecture are engineered together instead of separately. Both approaches may help, but neither is presented here as a fully proven commercial answer. The broader takeaway is more important than any single solution. As AI systems become denser, performance gains increasingly depend on whether compute, memory, interconnects, and packaging can operate together without being limited by their own heat output. Heat is only one layer of the semiconductor picture. Away from leading-edge AI silicon, STMicroelectronics has announced its third price increase of 2026, effective August 23rd, with lead times for power devices reportedly stretching to as long as 52 weeks. The company points to strong demand and rising costs. This matters because power semiconductors rarely attract the same attention as flagship AI chips, but they are essential across vehicles, industrial equipment, energy systems, and broad electronics manufacturing networks in Asia. The lesson is that semiconductor tightness is not uniform. It is possible for the market to focus on cutting-edge AI components, while less visible but foundational categories remain constrained at the same time. Supply chain resilience depends on the full component stack, not only on the most advanced nodes or the most talked-about chips. Even when components are available, supply chains still have to pass through trade policy without disruption. And that friction appears to be increasing. A White House report signals tougher U.S. enforcement against transshipment, meaning the routing of Chinese origin goods through third countries to avoid tariffs. The emphasis seems to be shifting toward documentation audits and closer scrutiny of transaction structures, not only shipping routes. For manufacturers using China plus one or broader multi-country Asian production strategies, that raises the bar. Geography alone may no longer be enough. Companies may need clear origin documentation, auditable value addition, and stronger compliance discipline to reduce risk when serving the U.S. market. In that environment, the ability to prove commercial substance, not just physical movement, starts to look like a competitive advantage. Even if manufacturing and compliance are in place, there's still a downstream physical limit: shipping capacity. Rising Chinese vehicle exports, particularly EVs, are putting pressure on the availability of pure car and truck carriers, the specialized roll-on, roll-off vessels used to move finished vehicles. Vehicle production can scale faster than this logistics layer because specialized ships cannot be built or redeployed overnight. This is best read as a signal to monitor rather than a fully established long-term conclusion. But it still illustrates a larger point. Export competitiveness is not determined only by factory scale, product pricing, or technology. It also depends on whether the transport infrastructure behind those exports can keep up. The final signal comes from a different part of the industrial landscape: geopolitical trust, translated into technology cooperation. Japanese Defense Minister Shinjiro Koizumi's August 2026 visit to India coincided with the launch of the two countries' first defense co-development project, focused on the Unicorn Integrated Mast System. No companies, budgets, or timelines are specified here, so this should be treated carefully. What matters is the change in form. India and Japan are not just signaling alignment or discussing procurement. They are beginning to test whether strategic ties can turn into practical co-development. That does not prove a major regional realignment, but it may serve as an early indicator of how defense industrial cooperation could evolve if political alignment is matched by execution. Taken together, these 6 signals do not point to one cause or one event. They point to a common pattern. Asia's technology and industrial momentum remains real, but the next differentiator is execution under constraint. In Southeast Asia, the question is which economies are tied more closely to the AI hardware export cycle, and which remain more exposed to energy pressure. In AI chips, the issue is whether thermal limits begin to slow practical scaling. In semiconductors more broadly, it is whether shortages in power devices interfere with deployment across industries. In manufacturing, it is whether supply chains can withstand closer custom scrutiny. In EV exports, it is whether logistics capacity can keep pace with production. And in defense technology, it is whether strategic alignment can be converted into actual co-development. For investors, the implication is straightforward. Asia Tech looks less like one unified theme and more like a set of selective exposures shaped by bottlenecks. Country selection within Southeast Asia matters. Semiconductor analysis needs to separate advanced packaging and thermal management from power device availability. Manufacturing exposure should be judged not only on cost, but also on compliance quality, origin traceability. EV competitiveness should be watched alongside specialized shipping capacity. And the India-Japan defense project should be treated as an early marker, with attention on whether it leads to named industrial partners or follow-on programs. Constraints do create risk, but they also reveal where durable advantage may be forming.